So next we're going to define exponents, or in other words, powers. We can take powers of numbers, or we can place exponents on real numbers, and it turns out we could also do it with matrices. And it turns out in order to give definition or give meaning to what it means to raise a matrix to a power, we're going to need to start with a couple of things. So let A be a square matrix for now. And remember, sometimes I'll articulate that by just saying let A be n by n. And I'll just indicate that the number of rows and columns are the same that way. And sometimes it can be a briefer way to articulate it, but in this case, I want to reserve the letter n for a different use. So I'm going to say and let n be greater than or equal to 1. So some positive counting number, like 1, 2, 3, 4, 5, or 12, or 17, something like that. Now we can define what it means to take A and raise it to the power of n. So you use the exact same idea that you would use if you were defining powers of real numbers. So what A to the power of n is defined to be is you just take A and you multiply it by A, and you keep on multiplying it by A, and you do that n times. So the number of times you multiply A by itself is completely determined by what appears in the exponent. Now, I'm going to let you think about this for now. Why is it, though, that I insisted that A be a square matrix? Right? This is probably the definition you would have expected for a power, but the fact that I insisted that A be a square matrix might not have been obvious. So I'd invite you to give that some thought. You can either you can pause the video, do it now, or you can just keep watching and put it on hold to think about later. It's totally up to you. But that's the definition of A to the power of n, where n is a positive counting number. But we can do more. We can still take exponents even if the exponent isn't a positive counting number. Like, for example, what if I wanted to take A and raise it to the power of 0? That's actually going to require a separate definition because that doesn't fall under this definition, because this required n to be a positive counting number. So what do you do if the exponent is 0? Well, what would you do in the case of raising a real number to the power of 0? Like if I went 5 to the power of 0. Let's actually write a reminder up here. If I had something like 5 to the power of 0, we just take that to be 1. Remember, if you ever have an exponent of 0, any number raised to that power is just 1. So, well, does that mean we're gonna say that the matrix A raised to the power of 0 is 1? That might not make the most sense, because we want the result of taking a matrix and raising it to an exponent. We want the result to be a matrix. So we need to have whatever we put here should be a matrix. So what's the closest thing to the number 1 that we have? And you might argue that the identity is the closest thing, right? Because it has the same multiplicative property in the world of matrices that the real number 1 has in the world of numbers, right? If you multiply any matrix by the identity, it doesn't change. Just like if you multiply any number by 1, it doesn't change. So that's how we're going to define a matrix to the power of 0. And if your matrix A is invertible, you can actually even say more. So let's say, and if A is invertible, and I'll just put a box around here to separate this, well, then you can raise A to a negative power. Right, I can go A to the power of negative n. And of course, negative n is a negative number, because if you go back to our original assumption on n, it was a positive number. So A to the power of n really is a negative power of A. And this only works if A is invertible, but you can do this. You can just define this to be, well, just take A inverse and raise it to the power of positive n. Right, so just change the sign of the exponent, but then change the base from A to A inverse, and that's how you can define negative exponents. But that only works, again, that only works if the matrix is invertible, because if it's not invertible, you're not going to have access to A inverse. Okay, so that's the definition of powers. I'm not going to grind through a bunch of examples, because it really just amounts to repeated matrix multiplication, which it really is, you're just grinding through arithmetic. So I'll let you practice a little bit of that on the exercise sets, but I won't fill up an hour of video time just working through examples, but I do want to talk about some properties. Okay, so let's start with an invertible matrix. and also some positive number or non-negative number. So, or we're widening the possibilities for n here. It's no longer a number that's greater than or equal to 1, and now it just needs to be greater than or equal to 0. So it could also be 0. So here are the three statements. So if we're starting with the assumption that A is invertible, we haven't mentioned it yet, but what about A inverse? We know A inverse exists if we assume that A is invertible, right? We know its inverse exists because that's really what it means to be invertible. It has an inverse. But what about the inverse of A? Is this matrix invertible? And that's a completely reasonable question. And it turns out the answer is yes. So this is invertible. But what's its inverse? Right? If you can say what its inverse is, that's enough to justify that it's invertible. So what is the inverse of A inverse? And it turns out the answer is just the original matrix A. So it's a symmetric relate. A has a symmetric relationship with its inverse. They are inverses of each other. Okay, so another property is that, well, if we start with the assumption that A is invertible, then any power of A is also invertible. So I can say then A to the n is also invertible. And what's its inverse? Well, I have to be able to say what the inverse is. And it turns out, if I want the inverse of A raised to the nth power, that's what this notation really means, just take the nth power of A inverse. Right? And really, what you're talking about is you're talking about this expression here. You're talking about A to the negative n. But this is a more natural way to write it at this stage. A to the negative n is a more compact way to write it, but this is the way you should think about it. If you want the inverse of the nth power of A, then just take the nth power of A inverse. It's probably, that's something worth saying out loud to yourself a few times, or even if you're just saying the words out loud in your head, just to practice turning the mathematical notation into ordinary language. It's a really useful thing to practice. And the third statement here is if we have some non-zero number, so some real number k, which happens to not be 0, then k times A, the scalar multiple of the matrix A multiplied by the scalar k, is also invertible. And what's its inverse? Well, the inverse of k multiplied by the matrix A turns out that if you take 1 over k times A inverse, it'll do the job. So if you want the inverse of a scalar multiple, just take the inverse of the underlying matrix, and then instead of multiplying it by the original scalar multiple, multiply it by its reciprocal, 1 over whatever that multiple was. Okay, so those are some properties, and I'll let you play around with those yourself to see why they're true. I'm not going to prove these to you. Most of them are straightforward. If you just work through a couple of examples, you start to see why they work. And I'll leave it to you. There's some exercises that in the suggested exercise set that correspond to these statements, and you can play around with them and start to see why they work. So I'll leave that for now, and we'll move on to another technique. And this is really powerful, and it's a really nice way to take advantage of something we did earlier in the course, and you'll see what I mean when I get there. But let's do the typical thing. We'll start with an invertible matrix. So suppose A is invertible, and I'm going to be specific. Well, first of all, if it's an invertible, you know that it's square, right? But I actually want to say invertible and n by n. I guess I didn't really need a comma there. Anyways, I just want to be able to refer to n, which is, remember, that's the number of rows and columns of this matrix A. So let's suppose I start with that. Well, consider the matrix equation that I'm about to write down. So AX equals B, just like we wrote earlier, right? And when I write something like this down, we're interpreting A as an n by n coefficient matrix, and you're interpreting X bar as a n by 1 matrix or a column matrix consisting of all the variables in some linear system. And then you have your constant matrix B, which is also an n by 1 matrix. And it really just consists of the column, which contains all of the constant terms from each of the equations in your system. So this matrix equation really corresponds to a linear system. And I'm going to change this period to a comma so we can actually add a bit more to the sentence. And I'm going to, well, but actually before we finish this off, what if I wrote this down? If I just wrote AX equals B over here, so I'm writing down just a copy of the matrix equation. We started with the assumption that A is invertible. So we have access to an inverse for the coefficient matrix A. So what happens if you multiply both sides of this equation on the left by A inverse? Almost wrote A inverse here again by accident, but I just tried to cover it up by putting that vector arrow over top of the x. So this is just AX from the original left-hand side is what's in brackets here, and then that B is down here, but both of them now have had an A inverse introduced as a left multiplying factor. Well, let's apply the associative property on the left-hand side. So I can shift the brackets and write this as A inverse A times x, and then the right-hand side, we'll just leave that alone. Right? And if I do that, well, by definition of inverse, this is just the identity matrix, right? And the identity matrix multiplied by anything doesn't change it. So the left-hand side is really just I times x, so it's just going to be x on the left-hand side, which is, remember, this is the column matrix consisting of all the variables of the linear system that corresponds to this matrix equation. So, and then on the right-hand side, you still just have A inverse B. So this actually doesn't look like we did much, but we actually, you could think of this as essentially solving the matrix equation, right? This is a way to write down the solution. So which has solution x equals A inverse B. And I'll even write an exclamation mark just to, I don't know, just to communicate the excitement there, because this is actually a big deal. What and why am I calling this a solution? Right? This is a weird way to write a solution. A solution ought to tell you what all the variables should have as values, or give you an assignment of values to each variable that makes each equation true, right? That's what we're expecting when someone says they have a solution for a linear system. But that's actually exactly what you have here, at least in a symbolic sense, right? You don't know exactly what the values are because I don't know what the coefficients or the constant terms from the matrix B are. You don't even know what the variable names are, but yet I claim that this still is a way to write down the solution. And to see why, let's start by just taking a look at the dimensions of everything that plays a role in this equation. So remember, x, the column matrix consisting of all your variables, that's an n by 1 matrix. If A is invertible and n by n, well then A inverse is also going to be n by n. I'll just squeeze that in up here, n by n for A inverse. And then B is an n by 1 matrix consisting of the constant, it's a column consisting of all the constant terms from each of the equations in the linear system that corresponds to this matrix equation. So if you multiply these, A inverse is n by n, and B is an n by 1. If you multiply them, the result is going to be an n by 1. So really, what you've got here is a column matrix here, which consists of all your variables. And then over here, you have a column matrix consisting of a bunch of values, because if the coefficient matrix A consisted of numbers, then so does A inverse. So A inverse is just a matrix of fixed numbers that has nothing to do with variables, and B is a column matrix consisting of all the constants from the linear system, so that consists of all numbers as well. So once you multiply these out, you're going to get an n by 1 matrix consisting of a bunch of numbers, and those are going to be exactly the values you want to assign to your variables to actually get your solution. So really what this is it's the solution written in column form, because you're writing your variables as a column matrix and you're writing their actual values as a column matrix. So this is actually a valid way to write the solution. Okay, let's look at an example, because that makes a world of difference. And again, I want to just keep this separate, because that's separate work just to justify this statement. But the example I want to start down here. Let's just solve a system. We'll keep it fairly simple, to like maybe like a 2x2 system, so 2 variables and 2 equations. So 3x minus 2y is equal to -1, and 4x plus 5y is equal to 3. Okay, so that's the system we're going to solve. And there's plenty of ways to do that, right? We could write out the augmented matrix and we could start doing row operations, and we could work our augmented matrix until it's in reducible echelon form, and then we could extract the solution that way, if there is any, because sometimes there's no solution. But let's instead apply the observation we just made, because, well, we don't know yet if the coefficient matrix is invertible, so we don't know if we'll be able to apply this. But let's start by taking this system and writing it in this form, and then we can check if the coefficient matrix is invertible. So let's convert this into a matrix equation. So if I say A is, I'm going to take all the coefficients, right? 3, -2, 4, and 5. And then my column matrix X bar, or X arrow, will consist of what? That's going to be a 2x1 matrix consisting of the variables X and Y. And then our constant matrix, or constant column, is going to be the 2x1 matrix consisting of the constant terms, right? So that's just a reminder on how you can map a linear system to a matrix equation like this. So this is now equivalent to AX equals B, and I'm talking about this linear system here. So if you can find a solution to this equation, you can find a solution to this linear system, and vice versa. They're the same problem to be solved. Okay, well, let's check if let me slide down just a bit. Let's check if our coefficient matrix is invertible to see if this observation applies. So let's talk about this matrix A. Remember how to check if it's invertible? Just multiply this number by this number, and this number by this number, and then subtract. So let's do that. Since 3 times 5 minus -2 times 4, well, what would that be? That would be 3 times 5 is 15. Then you've got 4 times 2, which is -8. So subtract -8, you get +8, which is 23, and that's not 0. So start over. Since this, which is the appropriate cross product of this matrix, is non-zero, A is invertible. And we can write down its inverse. We have a formula for its inverse, remember? And I'll just remind you what that looks like. If you have the matrix A given by A, B, C, D, if this product, AD minus BC, or if this expression, which is really formed from two products and subtracted them, is not equal to 0, then A inverse is going to be 1 over AD minus BC times the matrix D, -B, -C, and A. Right? That's what I'm talking about when I say the inverse formula. That's why we were computing this expression, because really this is the AD minus BC from this matrix, right? This times this minus this times this, and it was not 0, as we saw here, so that means the matrix is invertible, and we can write down its inverse using this formula. So we can write A inverse is equal to 1 over 23, right? I'm just going the 1 over AD minus BC. We worked this out and got 23, and now this matrix, flip the 3 and the 5, and just change the sign of the other two entries. So we'll change the -2 to a +2, and the +4 to a -4. So that is our A inverse. So we can use that to write down the solution like this, based on our observation, right? Based on this little examination that we did here, we don't have to go through these steps again. We know they work in general, so we can just apply them directly to get our solution, which is in this form. So let's write down our solution. So solution is going to be written as follows. It's just going to be A inverse times the constant matrix B. So what does that look like? It's going to be 1 over 23 times 5, 2, negative 4, 3. That's our A inverse. And then we're going to multiply by the constant term or constant column up here, which is negative 1, 3. And then once we work out what all this is, we'll know what all the values are. Because this over here is actually xy. So whatever we get for an answer, that will just be the solution written in column form. Let's multiply these matrices first. We can worry about the 1/23 after. So you have a 2 by 2, and you're multiplying it by a 2 by 1. So the first entry, 5 times negative 1 and 2 times 3, that's going to be negative 5 plus 6, which is 1. And then this next entry here will be negative 4 times negative 1 plus 3 times 3. So that's 4 plus 9, which is 13. So now this scalar, 1 over 23, that's going to multiply into the matrix, get applied to every entry through multiplication. So you'll actually have 1 over 23 and 13 over 23 for your two values in the 2 by 1 matrix. So I want to make a comment. Really, at this point, you could stop here. There's nothing wrong with stopping here. This is a way that technically this is the answer in column form because we started on the left-hand side of this equality chain, chain of links of equations. Here's an equation, here's another one, and they're all linked together. They start with the column vector x, which is all your variables, right, x and y, and you just worked it until you got a column vector of values, which really that's what this evaluated to. A inverse B just turned out to be these column of values. So that is your value for x, and that is your value for y. That's why this really gives you, that's why this really gives you a solution. So there's nothing wrong with stopping here, but just for the sake of us talking and clarifying, I'll just say that is, you can write it out this way if you like. You can say xy is equal to 1/23 and 13/23. If you want to write it explicitly with the variables afterwards, you can as well. There's nothing wrong with just stopping with this line. This is a perfectly reasonable way to communicate the answer, but this would be going an extra step to write it in column form. Okay, so that's how you can apply this observation. Is that easier than doing row operations? Maybe, maybe not, but it's nice to have a different point of view, right? And it's nice to see an example of how we can work theoretically with the inverse and prove a result without actually knowing anything about a matrix. Okay, so there's one more round of comments that I'm going to make in our next clip, and then we'll be done the section.